Channel Knowledge Map is a database that provides location-specific and site-specific wireless channel knowledge. It reflects the intrinsic channel attributes independent of transceiver activities and enables the paradigm shift from conventional environment-unaware communication and sensing to future environment-aware communication and sensing. The CKM is constructed by combining the location information of the user with the channel data attained by the ISAC system and stored in the database related to the user's location. CKM can provide location-based environment-aware channel prediction and inference. Taking the beam index map as an example, based on the constructed CKM, the base station can perform trailing-free beam alignment when the user enters the loss area to achieve uninterrupted communication services for users. The construction of CKM requires the user's location and channel information of the area. In the previous work, we have built a CKM prototyping system based on UWB localization. As one of the main application scenarios of 6G, ISAC can obtain the user's location and environment information without relying on UWB, GPS, or other external positioning systems, and its wireless resources can be used for user channel acquisition, enabling the construction of CKM. In the CKM construction phase, the transmitting USRP on the ISAC base station controls the phased array for beam scanning. The receiving antenna receives the echo from user and further processes the signal. User is equipped with a mmWave omnidirectional antenna, which measures and feeds back the strongest beam indices in real time, and feeds back the location provided by the LiDAR when necessary. The base station stores the received feedback information with the current location of the user on the server. The following table gives the system parameters. ISAC base station is composed of an USRP and mmWave phased arrays, and the communication user is composed of an USRP, a mmWave omnidirectional antenna, and a LiDAR. In order to verify the performance of CKM construction, a simple loss scenario is first considered. In the loss area, there are no obstacles. The user and the base station always maintain a loss link. Base station scans the environment in each frame, and the user measures the RSS during each beam scanning. The three strongest beam indexes and user's location are fed back to the base station to build the beam index map shown on the left. In the loss scenario, an obstacle is placed in the middle of the environment, which makes the user and the base station no longer maintain the loss link. This scenario is used to simulate the real environment, and the prototype will build the CKM based on it. In the application stage of Channel Knowledge Map, the base station senses the location of users and obstacles in real time through ISAC beam tracking. When user enters the unloss area, the optimal beam index of unloss is obtained by beam index map in advance, and predictive beam alignment without beam training is carried out to achieve communication coverage of users. ISAC base station periodically conducts environment sensing with the sensing frames, and performs initial access to the user within the experiment area to obtain its location. If the user will transform from loss to unloss, the base station will actively align the beam based on the pre-constructed beam index map to maintain the seamless connection of communication services and realize trailing-free beam alignment and robust beam tracking. In this experiment, a prototype of ISAC-based CKM is constructed for CKM construction. ISAC BS provides users with communication services while senses the environment and user location in real time. No additional time frequency resource overhead. realize the fast and efficient construction of CKM. For CKM application, realized real-time training-free beam alignment by constructing beam index map. No need to rely on external positioning systems.